I'm going to talk about running a cortical microcolumn in real time on SpiNNaker, some work we did recently. To give you a brief introduction to SpiNNaker for anyone who doesn't know, the idea is to make a 1,000,000 core machine with 1,000,000 mobile phone-like processors, ARM processors. And the idea, at least originally, was to model about 1% of the human brain, or 10 mice. It's probably more realistic that we'll be able to model 1 mouse at this point in terms of the software, but some of this work might change some of that. So what we actually do with a SpiNNaker chip has 18 cores on it. It has the main processor where we actually compute the neuron and synapse models. There's some data memory on there where we actually keep all the state and the stack and heap and things like that. There's some instruction memory where we actually then put our processing instructions. These are all quite small. There's the big part of SpiNNaker is that it has this special packet router. I'll get into that in a bit more detail in a minute, which is for sending around the spikes across the system, and it can send it across different chips between the different cores on this particular chip. And then we also have SD-RAM, which is connected to the chip as an extra on top of the chip, basically. And this holds things like the synapse states and also some activity logs, things like recording of voltages and spikes, anything like that. So I said I'd talk about the SpiNNaker Rita. So each chip has a hardware router. What happens is when a core wants to communicate with another core, it sends a packet, and the packet has a key in it. The key tells the router where to send the packet from now. So the key is keyed to the sender, not to the target. And the router then looks that up in a special table. It has a key and a mask, so you can send more than one spike might match one entry. So you could have like lots of neurons that all match the single entry in the table, so you don't need too many of them. And then finally, there's some data which tells you where you're actually going to send the packet. So it can either go to the cores on the chip, or it can go to the links on the chip to go out to other chips. So a typical multicast transmission might do something like this. So this is obviously not doing much multicast, but eventually it gets to the end there and it actually sends it out to multiple places. And that kind of all happens, it's fairly fast. Obviously that demonstration was very slow compared to what actually happens on the chip. You can get across the whole system in certainly less than a millisecond, probably less than 0.1 milliseconds in most cases. And that's across the whole 1,000,000 core machine when it's running in that configuration. There we go. You've probably seen pictures of these before. We now have our 1,000,000 core machine up and running. So the machine is made up of these boards of 48 chips, and then we put them all into these cabinets. So you get 24 boards in one of these racks up here, and they're all then wired together. However, we can actually let people use the machine in smaller sections, so you don't have to have the whole machine for one user at a time. We can break it down so people can use smaller parts of the machine as they go. So, what I'm actually talking about. The cortical microcircuit model, again, I'm not sure if everybody knows this, it's slightly less than 80,000 neurons. It's basically a representation of 1 millimeter squared of cortex. There's 285 million synapses approximately. It uses lift neurons. It runs at a time step of 0.1 milliseconds, which is one of the things that caused us issues in SpiNNaker because we designed it originally to run at 1 millisecond time steps. We also designed it to not have quite this amount of input per neuron. So all these things were extra challenges to us. The stimulation, there's two modes of stimulation. You can stimulate it with DC currents, which is nice and easy, or you can stimulate it with Poisson noise, which is a bit more complicated to handle. But and basically, when you do the Poisson noise, it's one Poisson for each neuron, so there's 77,169 Poissons as well. And this is sort of the arrangement of the cortical column. So it's arranged in these sort of 4 layers of excitatory and inhibitory feeding each other, and then lots of complicated interconnection between them. And there's more detail in papers if you want to know the actual subconnectivity. I think it ends up being something like we saw a model with 7,000 inputs into one of the neurons, so it's quite heavy. Again, we designed SpiNNaker for 1,000 inputs. We did actually do this, we ran this a while ago, not in real time, at about 20 times slowdown. We did some comparisons with Nest to show that we were getting the right sort of results. So yeah, to talk about that paper, we basically did this performance comparison, and we were looking at the energy used. This was our first go at trying to make this thing work on SpiNNaker. It took us a long time to get there. And it took us 2,901 cores to get it running at 20 times slowdown. The issue here was that it was slower than Nest, and it used about the same amount of energy as Nest per synaptic event, so it didn't seem very good. Following on from that as well, some people ran some GPU versions of this, and they managed to get two times slowdown from real time, and much better energy usage. So we were like, oh no, this isn't good for SpiNNaker. We wanted to do better than this. So what did we do? We basically had a Manchester CodeJam. So all those guys in Manchester got together and tried to work out a way of making this work. So one of the first things we did was to look at the load time. This was one of the critical things in being able to even evaluate this. To give you an idea, when you do a projection on SpiNNaker, you get population-to-population connectivity, turns into synaptic data. That synaptic data would then have to be loaded onto the system. This all sounds relatively easy. Unfortunately, for this model, it took about 1.5 hours to generate the synaptic data, and then 8 hours to load the data. So basically, you were running the simulation overnight to see what happened the next day. If it failed, you're like, okay, fix something, run it again. This wasn't productive in case of being able to get good turnaround time. So one of the things we did was convert the system to use connection description. So rather than actually generating the full synaptic data, you just generate a description, load that onto the machine, and get the machine to do the work for you. And this obviously speeds things up quite a lot. 1.5 minutes to generate the connection descriptions and 1 minute to load the data. Wonderful. There is an extra, obviously, 3.5 minutes here, which is where the machine is actually expanding this data. That's done in parallel across the machine. These are still very small cores, so they're very simple. They can't run very fast, so 3.5 minutes is pretty decent to get the whole network. So basically, this gave us a turnaround time of around 10 minutes to run the whole network at this point. This was fantastic. Still ran 20 times slowdown, but 10 minutes turnaround, so we could start experimenting with it. So the next thing we did was analyze the network a bit and say, why on earth is it we take 20 times slowdown? So we had the output of the network a bit like this. We looked a bit closer at what was actually happening in the spikes, and we get a fancy graph like this. The key things to look at in this graph, yes, I did have an arrow. The first thing we noticed was it was generating 4,000 spikes in the first time step of simulation. This was a little bit complicated for us to deal with, 4,000 spikes suddenly all at once. And we discovered that this was obviously a flaw in the way the simulation was set up in effect. It was basically set up a random distribution of membrane potentials at the start, a lot of which were over the threshold voltage already. So we immediately corrected that problem, got rid of that 4,000 initial spikes. That helped us a lot. That was actually a lot of our problem. We didn't realize this, of course. It just said, oh, we're overrunning for some reason. But evaluation showed us this. The second thing we looked at was how then during the normal part of simulation, how are the spikes distributed amongst excitatory and inhibitory being received into a population. So each neuron has an excitatory and inhibitory synapse, how many spikes we were getting to each one. And it was approximately 2 times the excitatory to inhibitory. So we thought, okay, we can maybe make use of this information. And I'll show you how. So in our normal way of operation on SpiNNaker, the traditional software as I call it, I don't know why you call it traditional, but the way we've been doing it so far is we run the neuron state update and synapse processing on a single core. You then also have Poisson noise. If you've got Poisson noise, that'll be on another core that's been fed into this neuron and synapse. In addition to this, oh yeah, so they're put on the board like that. In addition to this, we also have a problem of delays. I'll go into a bit more detail on this in a minute. But basically, we can only handle 16 time steps of delay on a core by default, just due to the memory that we have to play with this. So what we have is delay extensions, which allow us to get for longer delays into the network. And this network had, I think, up to about 14.4 millisecond delays, so it was quite a long distribution. You could obviously go longer, but that was sort of a reasonable distribution to get the right behavior. And yes, again, they were put onto the chip like this. So what we looked at then was, okay, can we actually instead of doing all the neuron and synapse processing on one core, can we break this down so that the cores aren't having to do so much work each on a single core in such a way that sort of fits in with the network? So I mentioned that double excitatory spikes to single inhibitory spikes. So what we thought was, let's make some synapse cores for which we've got 2 times the excitatory cores, which are these cores here, to 1 inhibitory core. Oops, freezing. Down here, which you can't see because it's red as well. And then they're all feeding into a neuron core, which is actually just doing the neuron state update at this point. In addition to that, we can also have a core still doing the Poisson noise, but now instead of communicating everything over the packet communication network, we can put all these on a single chip. We can actually use the SD-RAM communication at this point, so that helps as well. So yeah, basically we then have to break down the connectivity so that the inhibitory synapse cores actually only receives spikes from the inhibitory neurons. This saves it having to process spikes that it doesn't need to deal with. And similarly with the excitatory, we can then break down the connectivity to cores that are going from half the excitatory neurons go to one core and half the excitatory neurons go to another. So we just arrange this in advance, set up the communication so that that works. And then on the chip, we can actually get approximately 3 of these, fitting them into the actual space on each chip, which is quite useful as well. So we're sort of packing them in as much as possible. There are some extra things that go on this chip as well, system functions and monitor functions. So that's why we're only using about 15 cores here at this point. Yeah, so I mentioned you may have noticed that I didn't put delay extension cores in this. So I mentioned that I'd talk about this at some point. So the idea of our current delay model on the core, the receiving core, is that we have 16 slots. When you receive a spike, you put it into the appropriate slot, and then you rotate along the path basically until you get to the right one, and then you take it out of there and you start processing it on the neuron. So that's how we handle delays. When you've got 256 neurons on each core, there's 2 synapses, and you've got 16 delay slots, and they're actually 16-bit slots. You end up with 16 kilobytes of the memory used up on this. Now, we've only got 64 kilobytes on the core, so it's not this is taking up a fair amount of space already. It's not a huge amount, but we also have the neuron state as well. So with 256 neurons, they're taking up 10 kilobytes. There's all the other things that we're trying to do on the core as well. These are just the sort of headline numbers, but there's all sorts of other things going on. We have to store the stacks and things of that nature. So in this case, this is why we were restricted to the 16 delay slots on the core. But actually, if we start splitting this up on the synapse core, we don't have the neuron state anymore, so we can get rid of that. We can then have, say, 128 delay slots, and this is only taking up 32 kilobytes when we only have 64 neurons processing on the core. We do 64 neurons because it fits as a neat number at this point. This is about how much we can process on a single neuron core in 0.1 millisecond time steps. So we chose 64, it seemed to work quite well. This means we're only using about half of the DTCM now on the synapse cores for this, and the synapse cores are doing less work. They have less other data structures on there, so 32K is okay. And that means we can do all the delay now on the receiving side. We don't have to do delay extensions anymore. It's not quite as much as we used to do, but it gets us 12.8 millisecond delays. So that's good enough for the model. The other thing we've implemented is we make a hard real-time execution limit now. So we don't allow the system to overflow. We say it's going to run in real time. We're going to define it as such. And we define how the processing then works between the different cores, how the memory transfers are all working, and define them on very hard time limits. So basically, we define a time that we're going to take for each for each neuron processing. And because of the memory transfers are happening at the start of each of those times on the neuron core, and there's some memory transfers happening at the end of the synapse core to get that through in time for the neuron core to get it on the next time step, we basically have a smaller amount of time to do the processing in between. And we fix that. We work out how much time we need to do the transfer, and we fix that in advance and just say, okay. And then at the end of that time, if there's any extra spikes in the system, we just throw them away. We can't process them. We've run out of time. Job done. And the idea then is we can optimize this. We can say, okay, how many synapses can we cope with? We can add more synapse cores to make this work on a larger scale, for example. If we're throwing away too many spikes, we say we just need to re-optimize the network. But we've got that flexibility now. That's the design. A sort of aside at this point, another thing that we looked at in this network, once we've got the splitting done, is there's another bit of processing that we have to do, and it's related to how the reading keys work. Again, in traditional way that we did reading, we designed the keys like this, where basically you'd have your population would break down into a number of cores, and you would define a key that's been sent by each of these cores, and they would look something like this. So you've got a vertex being sending a key, core key I should have called it at this point, But actually we can rearrange the key structure so that it looks something like this, and now we actually have a population part of the key and a core part of the key, and it makes it a bit more useful later on. I can show you why this is. So if you imagine you have a core here that's receiving all the spikes from these other cores here, so this is about 312 cores here for processing 20,000 neurons. So in the cortical column you might have a 20,000 neuron population. You've got to receive all these things. The problem is you have to have a lookup table then to say, okay, if I receive from core 1, I've got to look at the entries over on the side here in this table. If I receive from core 2, I've got to look in this table. That's a big lookup table here, which has to be looked up with something like a binary search or something. That can take a bit of time. What we discovered was, because we'd done this population key instead, we could replace all those entries for all the different cores with just a population entry. And now you have, that looks up and it finds, you join up those tables in SD-RAM, and you can now look up linearly across this SD-RAM table. Now, of course, that's for a single population. In the microcortical column, we have 8, though. So now we only have to look up a table of 8 instead of 312 times 8, approximately. So obviously, this speeds things up as well. I did also mention that we're going to throw spikes away now when we run out of time. There is an issue with this, which is to do with the time synchronization across boards. Traditionally, SpiNNaker doesn't synchronize time. As it turns out, everything running on a single board will probably be synchronized in time, just because of the way the crystals work on the boards. But between boards, as soon as you're using more than one, things can drift. And there's 2 ways in this can happen. The first one is when we send the start signal. I can't see it properly, but basically that takes a bit of time to get across to the second board from the first board. What this results in is an immediate offset in the start time between the bits of simulation on one core and the other. Additionally, the clocks on the different boards are just not synchronized with each other, so they might not be running at exactly the same time. And so over time you get a bit of a drift in the difference between the clocks here. This sounds okay, so what? Does it matter? Well, the problem now is if you send a spike from something on this board, at the start of its time step, this board's just about to finish its time step, it'll just throw away your spikes at the end of the time, so that's not much use. So to avoid this issues, we actually introduced a time synchronization across the machine, where we could make sure that things weren't drifting. So we basically had a beacon going off, and it said, synchronize with this beacon on one of the boards, and then all the other boards would work out their drift from the beacon, and that was it. So yes, we synchronized the time. So what we end up is the resulting system. If we focus on looking at the processing done on one of the cores for this part of the network, we get an output look a bit like this, the horrible complicated graph. If we particularly focus on this part of the graph, we're basically looking at how many spikes did we actually have to flush, how many spikes did we have to get rid of at the end of simulation. And now we're actually getting rid of very few. So most of the time, there's a process spike versus flush plus processed up here, and you can see most of the time it's managing to keep on top of it. Every now and again you get a few spikes that we've had to throw away naturally, just because we've not necessarily got the tuning quite right. But the good thing about it is we still get the results that we were supposed to be getting. And of course we wanted to make sure that we really were still getting the results. It's easy enough to look at a graph like this and go, yeah, it looks about right, but it doesn't really tell you the true answer. So we did the full evaluation that we did in the cortical microcolumn paper again, and again, it matches up very well with the results coming out of NEST, so we're pretty happy with that. And then, of course, we wanted to look at the power on this. So one of the fun things that we did was we just measured the power on this suddenly very fast simulation, and discovered that our power meter that we plugged into the wall couldn't measure the power anymore. It was ticking over maybe by 0.01, and so it was very difficult. So what we had to do was then say, okay, can we run the simulation for, say, 12 hours? And we did this, and we were quite impressed that over that whole time, the simulation just ran, nothing died, and it completed perfectly happily. So we actually managed to get some decent power readings out of this. And yeah, we managed to get a much better energy per synaptic event. So we're now more on par with the GPU example. Now the GPU example was running at 2 times slowdown. We were running in real time at this point. So of course, there's a certain advantage. We're getting the same power usage for real-time operation here. That's at our current, again, that's as far as we've gone so far with this. That's not to say there's not more to do. So, in summary, we managed to run a cortical simulation on SpiNNaker in real time. And as we said, it is hard real time. This is that we're making absolutely sure that the time step is done. You can't drift on any time step. It's always kept in every time step. We've managed to do an order of magnitude reduction in the energy per synaptic event. And we've simulated this reliably for 12 hours. And that was just the number we chose, 12 hours. I'm sure you could run it for longer if you wanted to. We obviously want to keep on going with this. We want to scale this up to full, multiple microcortical columns. Now that we can do one, we should be able to do many. And of course, the fact that we are using that hard real-time constraint means that if you're using a real robotic application, you should be able to synchronize with it perfectly. And not have to worry about things drifting or one time step taking too long to process. It'll just throw away the spikes if it's suddenly getting lots too many. And that is it. Any questions?